Standard intuition suggests that to bend an object without any tipping or rotation, you must apply force directly through its center of mass, the centroid. In massive structures like bridges and aircraft, engineers replace solid blocks with thin-walled open sections, like these steel C-channels, to reduce total weight. We apply that same center of mass logic to this channel, placing the downward load precisely at the section's centroid. But the beam does not simply bend. Instead, it rotates along its own axis, warping under a load that was supposed to be perfectly centered. Traditional centroid physics is entirely insufficient here. This thin-walled geometry produces an internal torsional reaction that standard center of mass analysis fails to predict. This unseen torsion causes rapid metal fatigue and can shear through the heavy bolts used at structural connection points. These beams are critical in aerospace applications, where high-strength, low-weight open profiles are mandatory for the aircraft to remain airworthy. Failing to calculate this exact rotational tendency leads directly to structural buckling and catastrophic failure under normal operating loads. To eliminate this rotation, engineers analyze the internal stress distribution of the section to identify the mechanical source of the twist. As a beam bends, it stretches on one side and compresses on the other. This creates small horizontal force imbalances across the depth of the material. To resist these imbalances and hold the beam's layers together, the material develops an internal force called shear flow. In thin-walled members, this stress travels along the perimeter of the shape, functioning much like water moving through a pressurized pipe. We can trace this path starting at the free edges of the flanges. The flow begins at zero, growing linearly as it moves toward the center. Once it reaches the vertical web, it follows a parabolic distribution, peaking at the neutral axis. Shear flow is a dynamic path of force, and its behavior is dictated entirely by the specific geometry of the beam's cross-section. Look specifically at the horizontal top and bottom flanges of this C-channel. In the top flange, the shear flow pushes horizontally in one direction. In the bottom flange, it pushes in the exact opposite direction. These two opposing forces create a force couple. Much like two hands turning a steering wheel, they generate an internal torque. This internal torque is the mechanical cause of the rotation we saw earlier. It forces the beam to twist even when the load is applied to the centroid. The open geometry of the section converts its own internal bending stresses into a rotation that can eventually lead to a collapse. Because the internal torque is a product of the shape, it cannot be removed. Instead, we must introduce a counter-torque to neutralize it. By shifting the external load away from the center of mass, we create an opposing leverage that fights the internal rotation. The specific point where this balance occurs is the shear center. It is the only coordinate where a load produces pure bending without any twist. For symmetric shapes like this I-beam, the internal forces balance each other out naturally. In these cases, the shear center aligns perfectly with the center of mass. For structural stability, the shear center serves as the primary mechanical pivot point, overriding the traditional centroid. Unlike the I-beam, the C-channel is asymmetrical and remains inherently unbalanced. To counteract the flange forces in this shape, the shear center must be located outside the physical material of the beam, floating in empty space. In practice, engineers design brackets that reach out to this floating point. By applying the load here, the beam bends cleanly with no rotation. By calculating the internal flow of stress, engineers can safely utilize lightweight materials for complex designs. True structural integrity depends on locating the precise balance of these forces, rather than simply finding the center of the shape.